Hey everyone, it's Athena X. In the last video, we set up a classic linear regression problem and solved it by minimizing the average of the squares of the residuals, an approach called ordinary least squares, or OLS. Now we're going to derive a best fit line statistically. For this video, you got to know the fundamentals of probability, including PDFs, CDFs, conditional distributions, independence, and normal distributions. Let's repeat the setup from the last video with some important modifications. So you have n xy samples. But the difference this time is we're now assuming a probabilistic setup. I'll use capital letters for random variables and lowercase letters for specific values that the random variable can take. So we really have some random variables, xi. I is from 1 to n. One for each sample we take. Then for each sample, we have the random variable yi, which equals beta 1 xi plus beta 0 plus epsilon I, where epsilon I is now a noise random variable. And in particular, epsilon I is normally distributed with mean 0 and variance sigma squared. So once again, we are assuming that the true model is actually linear like this. The underlying y is beta 1 xi plus beta 0, and that there's noise added. We're still assuming that, we're modeling something linear. Okay. We also now want to assume that all the x's are independent, all the epsilons are independent, and that all the x's and epsilons together are independent. Formally, we say that the set of all the x's and epsilons are mutually independent. So this set x1 through xn and epsilon 1 through epsilon n, this set is mutually independent. Informally, this is just saying that no subset of these random variables affects any other disjoint subset of these random variables. In particular, no x is influenced by any other x, no sample affects any other, and no noise affects any other noise. And in fact, no choice of x affects any of the noises, and vice versa. For a more formal understanding, you can search about mutual independence of random variables. By the way, this kind of noise is called additive white Gaussian noise, often abbreviated AWGN. The noise just means noise. It's something obscuring our measurements. Gaussian just means Gaussian or normally distributed. White is an informal term, which basically means that the epsilons are uncorrelated. We actually have assumed that the epsilons are independent. That's what we assume here. And independence is actually a stronger condition than being uncorrelated. But for Gaussians, it's the same thing. For Gaussians, you're independent if and only if you're uncorrelated. The additive here means that the noise is being added to your underlying y. So if you have your xi, you get this kind of underlying y here, which is beta 1 xi plus beta 0. Then you get your plus epsilon I. And it's because of this plus that we get additive. If this had been a multiplication, for example, the underlying y times epsilon I, then maybe we'd call this multiplicative white Gaussian noise. Okay, so note that epsilon is an unbiased random noise, like in the previous video, but there's no longer a requirement that it's small. This sigma could be anything. But obviously, the smaller the errors, the more sure we are that we have a well-fit line. So going back to this yi, we have a random variable xi here, and yi is completely determined by xi and epsilon I. So yi is random. It's a random variable, but it is determined entirely by these two other random variables, plus of course beta 1 and beta 0, which are unknown constants. So for each sample xi, yi that we get, it's actually a sample of the random variables capital Xi and capital Yi. Finally, I'm also going to say that the xi are chosen independently. I'm going to explain what I mean by this in quotes. Independently of beta 0, beta 1. Now, beta 0 and beta 1 are not random variables. They are unknown constants, and there is a difference. And I'll get into this difference in a little bit, but for now what I mean is that regardless of what beta 0 and beta 1 are, they have no effect on the distribution of xi. And you'll see why this is important in a little bit. Now let's think about this. Let's say we have an example like this. Since the noise is Gaussian, centered on 0, we intuitively know it's much more likely that the true line is something like this, and that we get a bunch of small noises, than that the line is way over here, for example, and that we get a bunch of huge noises. Not only huge, but that they're all positive, and that they actually increase as you go to the right. Now remember, all the noises are uncorrelated, so there's no reason they should increase as you go to the right or left. So we intuitively know that this top line makes a lot more sense than this bottom line. Let's try to formalize this concept. So a line is specified by beta 0 and beta 1, which are unknown constants, not random variable. So if we're thinking about saying, well, let's choose the most likely or probable beta 0, beta 1, that doesn't make sense. So just to be explicit, if we say probability of beta 0, that does not make sense because beta 0 is not a random variable. Similarly for beta 1. Similarly for the joint of beta 0, beta 1 also doesn't make sense. And even saying something like the probability of beta 0 and beta 1 given the observed data, even this doesn't make sense because again, the xi, yi part is fine, but beta 0, beta 1 are not random variables. And if you want to learn more about this, you can look more into classical statistics versus Bayesian statistics if you want to do more research on that. So for now, let's think about why we think this top line up here is more likely than this bottom line, without talking in terms of probabilities of the betas. So what I said was, if the true line was this top line, then the data would make sense in that there would be a relatively high probability of seeing this data. And notice I said probability of seeing the data, not probability of this being the real line. But if the true line was this other line, then this data would not make as much sense, in that there would be a relatively low probability of seeing this particular data if this was the true line. Intuitively, what we're trying to say is that the probability of seeing the data, and by data I just mean these xi, yi's, given beta 0, beta 1 of top line, right? This is greater than the probability of seeing the data given the beta 0 and beta 1 of the bottom line. But even here, technically, we should not be saying this because this vertical bar is used to condition on random variables. But here, again, these are not random variables, so we don't want to be saying this. Instead, what we want to be saying is there's a notation we use for this. You'd say the data semicolon. I'm not going to write out beta here. I'm just going to shorthand this to top line. This is greater than probability of data semicolon bottom line. And in English, we don't say semicolon, we'll just say data given bottom line, perhaps. But when we say given with a semicolon, it means something different from given with the vertical bar. Here what we're saying is we can't use probabilistic math basically to describe this conditional probability. So we can't say, for example, a probability of, if we said data given top line, then you might be able to write things like this is equal to data and top line, right, divided by the probability of the top line. But we cannot do this because we're saying that we're using semicolon. So these laws don't work because there is no probability here in the denominator. That doesn't exist. None of this makes sense. Cool. So we want to pick the line that maximizes the probability of seeing the observed data. That's our guess. So we have the probability of the data semicolon the top line, data semicolon bottom line, and the same for an infinite number of potential lines. And we want to pick the line perhaps such that if that line were the true line, meaning if the beta is really worth those values, the probability of seeing the observed data is relatively the highest. In other words, we want to find argmax over every potential line, the probability of seeing the data given that that line is the true model. Cool. So this approach is called maximum likelihood estimation, or MLE for short. It's called this because this probability here is called a likelihood. It is a probability, but the probabilities here are not conditioning on a line, and it's not the probability of the line which we're interested in, because we can't say that, it's an unknown constant. It's the probability of the data in these alternate universes where suppose, this line is true and suppose another line is true. So these probabilities don't add up to 1, but we are interested in picking where this is maximized, and we call this probability, therefore, the likelihood. And we are going to, as our best guess, choose the line to be the line that maximizes this probability, even though, again, the line is a true, unknowable, unchoosable quantity. We're just using the argmax as a good guess. Okay, one quick note is that I wrote probability here, but really it should be a PDF or probability density function, since these variables are all continuous, not discrete. So we'll use PDFs going forward. Okay, so just a quick little refresher. For PDFs, if I say, there's a random variable, big Z, and I say I have f sub z of z, this is the PDF of the random variable z at the point little z, at that value. And let's say, for example, I have also another random variable, let's call it q. I can say, I have PDF of q at little q. And the little q, again, is just a number, which q could be. It's just some real number. So there's the bottom subscript here describes the distribution, the random variable of interest, and what's in the parentheses is what big Q equals. And here's the probability over the distribution of Q that it equals some value that Z happens to be, for example. And again, this is just some real number, but I'm saying what's the density, probability density around that value for the random variable Q here. And another general thing is that the PDF, right, at a certain value is equal to the derivative with respect to z in this case of the CDF of z at that value. And as a reminder, the CDF of z, this is where it ties into probability axioms. This is what's really well defined to be the probability that z, the random variable, is less than or equal to whatever value you pass in here. Cool. So let's go back to what we're trying to argmax over here and write that down. So more formally, we're trying to take the argmax over all beta 0, beta 1 of the PDF of, I'm going to write these as vectors here to indicate all the xi and all the yi of this is the lowercase x, the specific values they take on. Right? Again, all given beta 0 and beta 1. So we can rewrite this as the following. Using just the definition of conditional probabilities, we can say, hey, I can break the joint probability of overall x's and y's into just the x's, and the beta 0 stay everywhere. I mean the beta 0, beta 1. So we have just the x's, and then we have the y's given these x's. Here we use the vertical bar to mean conditioning on a random variable, so all the x's are these little x's, and then we use the semicolon for the beta 0, beta 1. One thing to note is that this here is a positive constant with respect to the betas. So remember I said earlier that we're going to assume the x's are chosen here independent of the betas. What that means for us down here is that regardless of what beta 0 and beta 1 we choose, this is always going to be the same number. And in general, that means we can just get rid of this term in the argmax. Why? So let's consider just like a random example here. Let's say I have something like this. And if I consider multiplying this whole thing by, say, 2, I would get something like this. And the argmax, which was here for the original function, right, that would be this point. Even when you multiply by 2, well, this is not drawn to scale, but if you multiply by 2, it would show up, the argmax would be the same, basically. Since if it was the greatest point before, even when you multiply everything by 2, it's still the greatest point. And that's why if you multiply by a positive constant, it doesn't change the argmax. If this was a negative constant, the whole graph would be flipped, right? And so now it would be it's not drawn very well, but it would reflect over to be the argmin instead. And this will come into play later, but for now we don't need to worry about that. So now let's write this again without this positive constant. And I'm going to split up this y vector here into its components. The cool thing is we can again use conditional probability, and we can break this up into each y separately. The joint distribution of all the y's is just y1, and then y2 given y1, and so on. So what this breaks down into is the PDF of y1 given the x's. Then you have y2 given the x's and the y1. And this goes on. And the last one is yn, again given all the x's, and conditioned on all the previous y's. Okay, so how do we break this down? Well, let's recall that yi equals beta 1 xi plus beta 0 plus epsilon I. Now, we can use independence. So we already know that all the x's and epsilons are mutually independent. Informally, that means any subset of the x's and epsilons are not affected by any other disjoint subset of the x's and epsilons. I want to explain that the yi are also mutually independent. Let's consider just y1 and y2, for example. y1 is just a combination of x1 and epsilon 1. There's the betas as well, but remember, we're just treating those as given. So just imagine I have a semicolon beta 0, beta 1 for this equation. y2 similarly is just a combination of x2 and epsilon 2. Since x1 and epsilon 1 are unaffected by x2 and epsilon 2, that intuitively also means that any combination of just x1 and epsilon 1 is also unaffected by any combination of just x2 and epsilon 2. Therefore, since the two y's are just combinations of their respective x's and epsilons, y1 and y2 are also independent. You can extend this reasoning to all the y's, not just y1 and y2, and show that they're all mutually independent. I won't show the formal proof here, as it would be a bit too much of a tangent, but this is a fundamental theorem in probability theory regarding mutual independence of random variables. By the way, you may have a question here. once you know a few y's, doesn't that give you some information about the true betas, which can then help you predict what the other y's are? Doesn't that make the y's dependent? Well, they do give you information, but that doesn't make the y's dependent because we're treating the betas as given. So what we're saying is that the y's are independent since betas are given as unknown constants. But something that's important to note, and we'll get more into later, is that even if the betas were random variables, if we conditioned on them using our typical vertical bar, saying given beta 0, beta 1, you could still say that the y's are independent given the betas, or conditioned on the betas. But for now, the important thing to know is that the y's are independent. And so by that logic, we can rewrite this argmax like this. This is the same as before. But for this next one, we don't have to condition on the y1. And this goes on until yn. And at this point, we can actually say even more using the same identity here, by the same logic. Since the yi is made up of xi and epsilon I, the question is, does knowing some other x help? So if you're interested in y1, knowing x1 helps. Of course, knowing epsilon 1 would help. But would knowing x2 or x3 or any of the other x's help? No, right? Because they have no impact on x1 or epsilon 1 because of the independence. And so each y is only dependent on its x and its epsilon and no other x. And so each of these here, right? Each of these, we can say that the y1 only the y1 conditioned on all the x's is the same thing as just saying y1 conditioned on x1. None of the other ones matter. And so similarly for y2, we can just, instead of all the x's, you can condition on just x2. And so we're going to use this trick to simplify this even more. So we have y1 given x1 and y2 given x2 dot 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 yn given xn. Cool. At this point, we're going to take this equation right here, and we're going to rewrite it in terms of epsilon. So the reason I'm writing it this way is to emphasize some intuition. Let's think about this argmax again. What we're trying to do is pick the betas, in other words, pick the line that makes the observed data the most likely. Given that we know some arbitrary x's, we're saying for all possible betas, given those betas and the x's, what is the probability of observing the observed y's? Well, the probability of observing those specific y's is just the probability of observing the first y, then the second y, and so on. Now, since we know the betas and the x's, we know the underlying y. That's exactly what the line is. If you plug in x, you go up on the line, that's the y. The only reason we observe something else outside of this line is because of the noise epsilon. The underlying yi is just beta 1 xi plus beta 0. And epsilon I is the difference between yi and this beta 1 xi plus beta 0. Intuitively, what this means is that the probability of observing the yi that you did is the same as the probability that the epsilon I was exactly the amount needed to account for this difference between the observed y and the underlying y. In other words, instead of thinking about the distribution of y, you think about the distribution of epsilon. So what does it take for epsilon to be exactly the epsilon I that you observed, instead of what does it take for y to be the exact yi that you observed? And I said probability here, but it's really all probability density, again, because these are all continuous variables. So what this means is that the PDF, the probability density of a yi given the xi, is the same as the PDF of epsilon I equaling yi minus beta 1 xi minus beta 0. What is this saying? The probability essentially that y was exactly what you saw given x is the same as saying, hey, well, if I had a particular value of x, epsilon I is just exactly what's needed to bridge that gap. That's how you get this. The probability of seeing your yi given your xi is the probability that the leftover part was epsilon I, which is a random variable, is exactly equal to this. But let's prove this more formally. So to prove it, you can't. This should make sense, but you can't exactly just say, oh, I'm going to plug in this inside this probability density function and solve for epsilon. I mean, that would intuitively work and get you the right answer, but you got to do a proof in terms of probability loss. So let's do this little proof here. So like I hinted at earlier in the video, the proof, you should use probabilities, and probabilities for continuous variables come from the CDF. So we can say that the CDF of yi given xi, this is equal to, by definition, the probability that yi is less than or equal to yi given that xi equals xi. Oh, and by the way, all of this should have semicolon beta 1, beta 0, but I'm not going to write it for all of these, just for the sake of time. So now at this point, we can replace this yi with the following. Just use the definition given here, or I guess we can use the definition up here. So this is capital Yi is less than or equal to lowercase yi, given xi equals xi. At this point, xi only appears here, and we're given what xi is. You can just replace this xi with lowercase xi. So you get beta 1 lowercase xi plus beta 0 plus epsilon I is less than or equal to yi. And now epsilon I is the only random variable. Right? Everything else here is given. It's a constant. So we can solve for epsilon I and write this as the probability that epsilon I is less than or equal to yi minus beta 1 xi minus beta 0. And what is this? Well, this is just by definition, the CDF of epsilon I at this particular point. Yi minus beta 1 xi minus beta 0. So now, if we take the derivative, right, of this and this, we get what we want. So this is proving that the CDFs are equal, but we want to show that the PDFs are equal. So we take a derivative, but with respect to what? Well, yi makes sense here, as we have yi on both sides, and if we take the derivative with respect to yi, we'll get the PDF of yi on the left-hand side. What about on the right-hand side? Well, we can apply the chain rule. The derivative of the right-hand side with respect to yi is first the derivative with respect to yi minus beta 1 xi minus beta 0. And the derivative of the CDF of anything with respect to that thing itself is the PDF. So that is just the PDF of epsilon I times, with the chain rule here, the derivative of yi minus beta 1 xi minus beta 0 with respect to yi, which is just 1. So I won't write that. So you might say that was a lot of work. I mean, I still basically just took this definition of yi and plugged it in right here. That's the only step I did. And it seems like after that, it was just capital F back to lowercase f. And that's right. But just to formally prove it, now you got to use probabilities and CDFs. You can't just plug into PDFs. And in fact, in more complex examples, if you just try to think about things in terms of PDFs, you might get the wrong answer. You have to really go into the CDF world, get the answer, and convert back to the PDF with the derivative. Cool. Now that we have that, I can rewrite this argmax in terms of the epsilons. So we have epsilon 1 being y1 minus beta 1 x1 minus beta 0. And epsilon 2, same thing, but with x2 and y2. And again, dot, dot, dot. Okay, And just to make this a little bit more nice and neat, I can just write this as the product from I equals 1 to n, this big capital pi thing means product, of the PDF of that particular epsilon I at yi minus beta 1 xi minus beta 0. And let's review, what is epsilon I? Epsilon I is normal, 0 and sigma squared, and that means the distribution of every epsilon I, they're all the same, equals 1 over sigma root pi, this is just the definition of the normal distribution, times e to the negative half epsilon I over sigma squared. So if we plug in this distribution here into this argmax, what do we get? Well, we get argmax over the betas from I equals 1 to n of this formula, but instead of little epsilon I, we have this whole expression. So it would be 1 over sigma times square root 2 pi times e to the negative half times yi minus beta 1 xi minus beta 0 all over sigma and this thing squared. Now again, just like before, this is a positive constant, so we can just get rid of it. It does not affect the argmax. The next thing we can do is, I'll just rewrite this. The next thing we're going to do is we're going to take the natural log. Okay, why can we do this? Obviously, we can't just be doing whatever we want to this expression. We have to make sure that this will not change the argmax. So the first thing to note is that, is this even a valid operation? Natural log is defined for only positive numbers. First of all, intuitively, since this is a probability, it's going to be positive. But also e to any power is going to be positive always. So this is definitely valid. Let's draw what natural log looks like. Looks something like this, right? And it crosses over the x-axis at exactly 1. This x and y has nothing to do with our x's and y's here. I'm just drawing a graph, an xy graph. What kind of a function is this? This is a monotonically increasing function. What does that mean? What this means is if the input, for two inputs, if one is at least as large as the other, this implies that, in our case, natural log, if you take the natural logs, that relationship still holds true. And that should make sense if you look at this graph. If I have 2 points and x1 and x2, if x2 is more to the right, so it's bigger, then natural log of x2 is going to be higher. That should make sense. So if this is x1, for example, and this is x2, then this is natural log of x1, and this is going to be natural log of x2, and it's going to be higher. And so what is the argmax? The argmax is the betas that make this at a maximum, right? So if I picked a beta such that this was at a maximum, that means if I took the natural log, it's still going to be maximum because it was already higher. This is our x. This is our x here. And I picked the highest possible x I could. Then if I take the natural log, according to this logic here, even after the natural log, this should still be higher than the natural log of any other x because of this monotonically increasing property for natural logs. The basic idea is, since this doesn't switch the relative ordering of points, it doesn't change the argmax. Whatever was the maximum before, applying natural log will still keep it higher than all the other points. So what happens if we take the natural log? You have a product in here, and natural log of the product is the same as the sum of the natural log. So you can rewrite this, the sum from I equals 1 to n of the natural log of each of these terms, e to the negative half yi minus beta 1 xi minus beta 0 divided by sigma and all that squared. And the natural log, and you have e, those two cancel out. So what you're left with is just this part, which I'll write out. Now we have from I equals 1 to n, we have negative half times all of this. Yi minus beta 1 xi minus beta 0 over sigma and all that squared. Now, by the same logic as before, we have 2 is a positive constant, so that's gone. We can remove that. Sigma is also a positive constant. And the last thing is, like I mentioned before, if you have a function and it looks something like this, and if you argmax here, if you reversed this function like this, if you basically took just the negative of it, well, now this point that used to maximize the function is now minimizing the function. So the argmax becomes the argmin when you negate a function. So you can actually, I can remove this negative sign, and I can make it a positive, and just flip the argmax to an argmin. And then now this minus is a plus. So this 2 is gone, we just have a 1. This sigma is gone, so we just have yi minus beta 1 xi minus beta 0. This should look familiar. This is the OLS, ordinary least squares, loss function. And you can solve for beta 0. I'll put a hat to indicate that that's the argmin. And in the last video, I don't remember, I might have put a 1 over n here, but it doesn't really matter, again, because it's just a positive constant. It won't change the argmin. It won't change the betas that we get. So what is the point of doing all this? The purpose of this is to really show the MLE approach and MLE justification of OLS. What I mean by justification is that instead of just choosing the squared error and minimizing it as some arbitrary choice, you can see that, hey, under some assumptions, you still have to assume that you have Gaussian noises and some independence assumptions. Not only is the squared error a potentially reasonable thing to do, but it's actually, in some sense, the optimal thing to do. That under some assumptions, it actually would give you the betas that would make the observed data the most probable out of all possible betas and out of all the data you could have seen. And if we want to review what these assumptions are, you'll notice that they are kind of strict. I mean, we have mutual independence of all these errors and x's, and that the x is not at all affected by the betas, and that the noises are all, they all have the same variance. So these aren't trivial assumptions, but they sometimes can hold true, or they can be good approximations. In the upcoming videos, we'll go over different kinds of assumptions you can make, but the key point is that MLE still holds. So even if you had different variances here, even if these epsilons were not independent from other epsilons, and even if they weren't even Gaussian, they could be something else, it's still often possible to set up a situation like we have here, where we say I want to do maximum likelihood estimation, where I find the line, the parameters beta, that maximize the probability of the observed data. We'll do some variations on this and extensions of MLE and even other frameworks besides MLE in the upcoming videos. Until next time.